today kind of is a big day. All right, so finally we're going to leave the world of electricity, right? And before we leave it, we need to, let's recall what we've done there in the world of electricity. First, we introduced some foundation. We introduced some foundation, some fundamental equation, and we spent quite some time introducing those fundamental laws. Then, once we laid down the foundation, we started searching for the some ways of simplifying our life. And we introduced the energy approach. Right? And then we just went into applications. We started applying fundamental stuff in circuitry, okay, simple circuits, of course, very simple circuits, right? And that's where we finished. And now it's time to move into a different world of magnetism, right? We've been in the world of electricity for almost a couple of months. It's more than enough, right? Okay, so now it's chapter 29. And now let me show you this small sort of like a movie, cartoon, in order to see the evidence of the something new, evidences of magnetic field. Okay, let me start it. So what do we have here, effectively? We have two electrons here, stationary. Okay, blue and green, but they both electrons. And of course, first I'm holding them, and then I will release them, and of course they will start repelling each other, and we will see by how much will they repel after a certain period of time. Right? So that will be the first system, and then we will compare those results, or that results, with the results produced by these two electrons. So, but now these electrons are moving that way with velocity v0, right? And then we will compare the results by how much this pair of charges will be displaced and by how much those two electrons will be pushed apart. Okay, so let's look first at these two stationary electrons. And of course, we know right now, after we discussed electricity, we know that these electrons will be moved, will be pushed apart by the electric force. Right? Of course, they create electric field, and then as a result, electric force appears, and of course, that force will push them apart. Okay, so let's look at first stationary electrons. Right? And after some time, they will be displaced by that distance, right? So now let's compare this displacement by the result. Let's compare what we're going to see from these two moving electrons, right? Okay, so and surprise, surprise, the results are different. When electrons stationary, they are displaced by a larger distance than displacement produced by the electrons which moves. How come? So it looks, obviously there is something else, something additional happening when electrons move, right? Which we're not aware of, right? There's something additional happening between these two moving electrons, right? So, and basically something like this, or maybe this, of course, researchers observed 300 years ago, or 200 to 300 years ago. And of course, back then, they were sort of at the point where they had to make a decision. How to model this, how to describe this, right? So there were two ways. First, they could just adjust electric field, just adjust somehow electric field for these moving electrons. That was the first approach. The second approach that they could take, they could introduce a new field, magnetic field. So on top of the electric field, moving electrons produce magnetic field, and as a result, there will be two forces, right? Electric force and magnetic force, and since they act in the opposite direction, so as a result, the outcome different. So which approach take? Okay, so for whatever reasons, researchers back then decided to go with an approach of introducing a new field, magnetic field, instead of somehow adjusting electric field, because you need to understand, we're just trying to model the nature, right? Of course, you can model the same thing using different approaches, right? So, for whatever reason, people decided to introduce magnetic field and use magnetic field. So in this case, if you have stationary electrons, only electric field is present and electric force, so they repel by this distance. But when electrons travel, there are two magnetic fields, electric field and magnetic field. And electric force repels them, but magnetic force will attract them slightly, right? So as a result, the net displacement is smaller, right? So it's one of the evidences of presence of the magnetic field presence, right? And as I said, researchers, for whatever reasons, decided to model it by introducing magnetic field, right? And the major point, only moving charges can produce magnetic field. When first two charges were stationary, they did not produce magnetic field. Right. Okay, so now, oops, right. Okay, so now let me repeat again. So if you have a charge and it produces it produces electric field, it doesn't matter if a charge is stationary or if charge moves. In both cases, electric field is produced. But magnetic field can be produced only by a moving charge. If a charge is stationary, no magnetic field, only electric field around. But if a charge starts moving, then two fields will be produced, electric and magnetic. Right. So moving, so and you know what? Everything in the world of magnetism is sort of like in dynamics. Like now we see that in order to produce magnetic field, a charge must move. So it must be in dynamics, right? And then in a few classes, when we will introduce magnetic force, again, similar situation. In order for a charge to experience magnetic force, charge will have to move. Otherwise, it will not experience magnetic force, right? So everything is in dynamics in the world of magnetism, right? Okay, so now, so the basic system, moving charge produces magnetic field. So as a result, we can identify three systems which can produce magnetic field. Okay, which produces magnetic field. First system, all right, just a point charge. Point charge, it moves. As a result, it will produce magnetic field. We're going to use letter B capital to denote magnetic field. Then the next system, what if you have a bunch of identical charges moving in the same direction or drifting in the same direction? What is that? It's a current. So of course, current must also produce magnetic field because it consists of a bunch of identical charges drifting, moving, right? Each of those charges produce magnetic field. So as a result, overall, current must produce magnetic field. Okay, so that's the second system which we're going to discuss, right? And the last system, a permanent magnet, must also produce a magnetic field. But of course, a reasonable question. Every time there must be charges, moving charges, right, in order to produce magnetic field. We see a moving charge here, we see moving charges there. Where are the moving charges in a permanent magnet in order to produce this magnetic field? And in order to see where are the moving charges, we need to recall a classical model of an atom, right? You remember what at the beginning of the semester I mentioned that several times. Of course, it consists classical model of an atom. It consists, of course, of the positively charged nucleus, and then around that nucleus there are orbiting electrons. Orbiting, what does it mean? Orbiting, it means moving electrons, right? And under certain conditions, right, only for certain type of materials, there is a non-zero net magnetic field. But effectively, a magnetic field comes from orbiting electrons, moving electrons, right? So that's the source of the magnetism produced by the permanent magnet. Magnetic field produced by a permanent magnet. Okay, so now we're going to discuss almost all these systems, all right, although most of the time we're going to talk about this current producing magnetic field. But first, in order to introduce some basic ideas, right, some conventions which are essential in order to live comfortably in the world of magnetism, we're going to use a permanent magnet in order to introduce, as I said, some basic ideas and conventions. So let's look at permanent magnet. And then by the end of the class, we will introduce fundamental law which allows us to find magnetic field produced by a current. Okay, so first, as I said, yeah, let's look at a permanent magnet and some first simple observations, right? Okay, so first, we all know, because we all played with magnets and play with magnets, right? We all know they interact. And of course, you know that there are two poles, north and south pole of a magnet. We're going to talk about poles in a few minutes, but now let's assume that we know that they have poles, right? And of course, we all know that if you take two like poles, right, north and north, for example, right, and try to bring them close, of course, you will feel that they repel each other. Of course, you all know that, right? So, and I feel it. They repel. It's difficult to, okay, possible, but difficult to bring them close, right? So, like poles repel. Just an observation which must be mentioned, right? Then, second observation, of course, opposite poles attract, right? So, if I take opposite poles, they attract. I can easily bring them together, right? So these are observations, right? Sort of, yeah, they behave like a positive here, for example, like charges, right? You remember, like charges repel and opposite charges attract. So it's something similar, right? There are similarities. There are similarities. Now, what's next? Okay, let's say for the first time in your life, somebody gave you a permanent magnet and tells you that there is a north pole and there is a south pole, right? So after playing with this magnet, so what should be your sort of like a next reaction? If you know there's a north pole and south pole, just normal reaction, natural reaction of any human being, right? What if I break it? Will I get separately north and south pole? I guess that was the reason behind dividing the Korea country into two, right? I guess in an attempt to see if there are opposite poles of the country, like north and south, and actually they happen to be very stable, right? North Korea and South Korea. All right. Anyway, so if you break the magnet into two pieces, I don't know, fortunately or unfortunately, I don't know what to say, right? It's just what we observe. If you break into two pieces, you will see two smaller full magnets, full but smaller magnets with both poles, south and north, and again south and north. All right. Okay, maybe just a bad luck. Okay, if you break it one more time, both of these magnets, this one and that one, again, you will end up with smaller, larger number of smaller magnets. And again, all of them are going to be full magnets, having both poles south, north, and south, north, right? It doesn't matter how many times you're going to break this magnet, you will never get separately south pole and separately north pole. They don't exist. But at this point, I have to emphasize, okay, maybe I should let me open this, right? I have to emphasize on one thing. It doesn't mean that magnetic monopoles are impossible. No one has proven that. It doesn't mean that magnetic monopoles are impossible, right? It's just no one has ever seen them, observed them. As a result, if we don't see them in our life, of course, all our equations are written using that fact that there are no magnetic monopoles, right? Actually, let's compare with the world of electricity. Did we have or do we have electric monopoles? Of course we do. What is effectively a positive positive point charge? What is it effectively in fancy words? It's a electric monopole. Positive electric monopole. What is a fancy name for a negative point charge? It's a negative electric monopole, right? So yeah, electric monopoles do exist, but magnetic monopoles, so far, no one has ever observed them. Right? But again, yeah, I emphasize, it doesn't mean that they're impossible theoretically, right? And actually, still, plenty of research, okay, not plenty, several of research groups, they still trying to find those magnetic monopoles. And of course, if you, for example, manage to find magnetic monopole, next year Nobel Prize of the next year's Nobel Prize will be yours immediately, right? You will be famous, right? Olney Hall will be named after you, and university will be proud that you were a student here, right? It's a big thing. And I'm sure that plenty of you watched that sitcom, The Big Bang Theory. Even I watched a few seasons, right? Not the last one, right? And you remember in one of the episodes, Sheldon Cooper got the NSF grant to go to the pole, I think South Pole, right? I don't remember, right? In an attempt to find, he was planning to find magnetic monopole, right? And you remember how happy he was when his friends faked data for him, right? Of course, he didn't know that the result that data is just a junk, right? But he was happy because he knew that pretty much Nobel Prize is his, right? Because it's a very big step in physics, very important step, right? Would be, and of course you remember how much he was crushed. Um, Puts the helium in his office, right? Okay, I was just reading the comment, right? And he was so crushed that he left the university and went back to his hometown in Texas, right? I'm just trying to emphasize that, yeah, it's a very big thing if somebody manages to find magnetic monopole. But so far, no one has ever seen them. Okay, so next, now we need to come up with a very important convention, right? Again, more conventions, right? Because we're laying down the foundation of magnetism. And of course, there will be conventions, there will be now fundamental laws again, right? Okay, so first of all, so now we know that magnetic field exists, right? So, and we decided to take that approach, introducing magnetic field. And of course, the logical question, how can we detect magnetic field, right? And again, basically the question is about which system can be used as a probe system. You remember the same question we raised at the beginning of this semester when we started moving in the world of magnetism, right? And back then we used the small positive probe charge, right, as the probe system. Now we have to introduce something similar here. And of course, what are the requirements for the probe system, for a probe system? First of all, it must be small, so that when you measure or detect magnetic field produced by some system, you would not change that system significantly, right? First, and of course the second, your probe system must respond on the presence of the magnetic field, right? So as a result, what can that be? And I think it should be a small permanent magnet. Of course, this is big, right? So small permanent magnet, right? And where do we have small permanent magnets in our everyday life? Compass. Compass needle is the probe. We can be used as a probe system. It is small, and of course, it responds on the presence of the magnetic field. Right? It aligns itself accordingly. Right? So, by convention, so we are going to use compass needle as a probe system to detect magnetic fields. All right. Okay, so now the next. So we decided which on about we so we've decided which system can be used as the probe system. Now next, of course, we all know that one side of the compass needle is called the north pole, north magnetic pole of the compass needle, and of course the other side is the south pole. why and which side of the needle should be called as the North Pole. And basically over here, we need to introduce a very important convention. And this convention, frankly speaking, is not that is not about the kind of physics. It's more like a introduced more like a from the way we use the compasses, right, in our life, right. It's not convention was not introduced from the point of from the physics point of view. Okay, yeah, that's what I was searching. It wasn't introduced from the physics point of view. Look how and this convention was introduced. Okay, so in order to introduce that, let's bring the Earth into this game, right? So let's assume that this is our, where is it? Okay, here, our Earth, right? And a few pieces of the Earth. Of course, it spins around axis of rotation. So let's say this is the axis of rotation. And of course, this is our north geographical pole. Emphasize, geographical pole. And of course, the other side, south geographical pole. And then, how do we usually use a compass? How do we usually use a compass? And or how did people use compass in old days? All the time we use it to find a direction to the north geographical pole. That's how we use the compass in our everyday life, right? In order to find a direction to the North Pole, right? Geographical pole, North geographical pole. As a result, so normal reaction of any normal human being, right? If every time you use the compass needle to find direction to the North geographical pole, how should you call that side of the compass needle? It makes sense to call that side of the compass needle as the North Pole of the needle. North Pole. And of course, it's a north magnetic pole of the needle. So that's at this point we're introducing convention, right? So that's how we decide which side of the compass needle is called or should be called the north magnetic pole, right? Because that side of the needle all the time points to the north geographical pole. And again, you see, basically this convention is barely connected to physics, right? It's more like a from practical approach. Right. Okay, so now after introducing this convention, right? So now, as a result, as a consequence, we can label or name magnetic poles of the Earth. Of course, we all know that the Earth has a magnetic field. And if you ask what is the reason of this magnetic field, the explanation is reasonably simple. Of course, we all know that inside of the Earth there is a molten iron core, right? Basically, it's sort of like a liquidy substance, right? High temperature, and of course that substance has, of course, tons of charges, right? And of course that liquidy substance has some currents, right? Sort of like Gulf streams in oceans, right? In ocean, right? And of course, currents, those currents move charges. So basically like a currents, and those moving charges produces magnetic field around the Earth. At least that's how it is. The presence of the magnetic field is explained now. Okay, so now we need to come, as a result, we need to label poles, magnetic poles of the Earth, following this convention, right? Okay, so let's assume that, not assume, but let's represent magnetic, the Earth is basically a permanent magnet, right? Let me draw this, you see a rectangle, basically like a permanent magnet, right? So, and you see that pole and this pole, right? So now we need to use the observation which we discussed like a couple of slides ago. Opposite poles attract. And of course, like poles repel. So if opposite poles attract, so since North Pole of the compass needle is attracted to that side of the Earth, it means that this side of the Earth, of this magnet, is the south magnetic pole of the Earth. north gets attracted to the south, right? So it means that if this is north magnetic pole of the needle, that should be south magnetic pole of the Earth. And of course, the opposite side is the north magnetic pole of the Earth. So you see, we have two types of poles, geographical pole and magnetic pole. Okay, poles, geographical poles and magnetic poles. And you see they are flipped. Where we have north geographical pole, there is a south magnetic pole, and where we have south geographical pole, there is a north magnetic pole. And of course, they're slightly offset. All right. And actually, you know what? A few years ago, I watched, you know, that famous show Top Gear, produced by BBC with the old crew, all right, with Jeremy Clarkson. And in one of the episodes, they traveled to the pole by car, right? It was an interesting show, right? And of course, since yeah, Jeremy Clarkson and James May, and of course, since they actually reached the pole, right, their names were added to the list of people who managed to reach the pole. I went to the Wikipedia to see that list, right? And of course, in the show, they didn't say much about poles, right? But in the Wikipedia, it was written that these guys, all those people, they reach a point where the south magnetic pole was in 1996. And back then, and that point is like a few hundred miles away to the north from one of the Canadian islands. And since then, what, 20, 24, 25 years has passed, right? And now south magnetic pole is a few hundred miles away from that particular point. All right. So I'm just trying to make a point that these magnetic poles, they drift. And of course, now if you hear that somebody reached, again, the pole, read carefully which pole. Is it actually North geographical pole? Because North geographical pole, it's like 1,000 miles away from the South magnetic pole, if not more now. All right. And yeah, these magnetic poles, they drift. Maybe after a million years, I don't know, maybe these poles will be flipped, right? Who knows, right? No one can predict that, right? Okay, so geographical poles and magnetic poles. So, and now the last piece. So since we use compass needle as a probe system, right, to probe magnetic field. Now, what about direction of the magnetic field? Okay, let me open it up, right? So you see the north pole of the compass needle, you see this north pole of the compass needle gives us all the time direction of the magnetic field. So if north pole of the needle shows that way, so that's the direction of the magnetic field at that particular point. If north pole shows this way, that's the direction of the magnetic field at that point. Right. Okay, so these are three major points. Probe system compass needle, convention about the names, right? Which side is north pole, which side is the south pole, and then direction of the magnetic field is given by the direction of the north pole of the compass needle. Right. Okay, so now after this, it's time to introduce magnetic field lines. But you know what? Of course, it will be done in the next slide. But in order to make this picture sort of like a full, complete, let me open up a few magnetic field lines. Then picture would look better. Okay, you see? Definitely it's getting better. Okay, now it's complete. So now we need to introduce these magnetic field lines. And the idea behind magnetic field lines almost identical like the idea behind electric field lines. Again, magnetic field, of course, is invisible, so it's a good idea to introduce some lines which can be used to visualize magnetic field. So by just looking at those lines, you can say immediately, okay, their field is stronger, their field is weaker, direction of the magnetic field at this point this way, at that point this way. It's very, very practical. Right? It's very, very useful. Okay, so let's introduce them. And so how can we draw them? Using the probe system. Like in the case of electricity, right? You remember back then we used the small positive probe charge. You would position at a certain point, find find the electric force, divide by the value of the probe charge. But now we need to use our compass needle. Position at a certain point, direction of the North Pole, give us a direction of the magnetic field. Then move to the next point, next point, next point, next point, right? Create a bunch of vectors, then connect them, introducing magnetic field lines. All right. So let's assume that you probe and map magnetic field produced by a permanent magnet, right? By a permanent magnet, you will get something like this. Okay, let me open it. Where is it? Yeah, here. So you will get something like this, right? Okay, so first of all, you see, it looks like as if magnetic field lines started from the North Pole. It's sort of like a positive charge. You remember in the world of electricity, all the electric field lines started from the positive charges and ended on the negative charges. Here it looks like the magnetic field lines from the North Pole starts from the North Pole and end at the South Pole. But it looks like. You see, all these lines, they go through the permanent magnet. All these lines form closed loops. It's a consequence of the fact that no one has ever observed magnetic monopoles. Okay, we can say that they don't exist, right? It's a consequence of the fact that magnetic monopoles do not exist. So all magnetic field lines form closed loops. If you manage to find one of the lines which are not closed, yeah, most likely it's a mistake, but it's still possible that you found the magnetic monopole, right? But all the time, magnetic field lines form closed loops, right? All right, but again, it looks like as if magnetic field lines started at the North Pole and end at the South Pole. All right, so then what else? Yeah, then what about how can we get information about the magnetic field from the magnetic field lines? The same like in the world of electricity, or the same like with the electric field lines. So magnetic field, let's say you want to know the direction of the magnetic field at this point. Magnetic field is tangent to the magnetic field line. The same like with the electric field lines, right? All right. And again, you see, north pole of the compass needle give us direction of the magnetic field. Okay, at this point, for example, right, again, magnetic field is tangent to the magnetic field lines. Magnetic field line. The same here, I can draw a few right, B's, right, magnetic field, tangent. Okay, so that's how you can get, of course, direction of the magnetic field. What about strength, magnetic field strength? The same, in the density of lines. So if you take, for example, this point, so density of lines is higher, so magnetic field is stronger. If you take, for example, region over here, density of lines is smaller, so of course magnetic field is weaker. So lots of similarities from the world of magnetism, or from the world with the world of electricity. Lots of similarities. Okay, and there's a typical demonstration. Usually I use a different device, but right now it's in a stock room, right? Locked up. All right, but a typical demonstration, right? If you take some liquid, well, some oil maybe, or water, right? And if you spread some iron filings on the surface of water, right? And then put a magnet, permanent magnet. Of course, those pieces basically of iron, right? Small pieces of iron, right? Filings. Of course, effectively they're small permanent magnets, basically like compass needles, right? And of course, they will orient themselves, like here we see on this picture. They will orient themselves along magnetic field lines. Right? As a result, they will form and show us lines which represents magnetic field lines. Right? So, and you see that on this picture. Right? Okay, so these are some basic ideas which we need to know, and some and the convention which we introduce. And now, what's next? Okay. So now it's enough, and now we need to start introducing fundamental equations, because again, we're all here engineers, right? Physicists, chemists. Of course, we need to deal with equations at the end of the day all the time, right? But before we start writing the equations, we need to recall some conventions from Physics 1 and a very important mathematical tool. We already practiced it in our recitation classes. Some of you, I think 3 sections or 4 sections, you will practice it in the afternoon today. But let me quickly again mention them. So first, from now on, in every problem, we're going to have vectors, mutually perpendicular vectors pointing in different directions. For example, one vector will be this way, one vector that way, and one vector, for example, up. So every time, if you try to draw 3 mutually perpendicular vectors on a surface, of course, one of the vectors will be all the time pointing out or in. So how can we show that vector on a piece of paper? Right, you've seen it before. Let me quickly remind you. So if you see crosses, it means a vector points into the page or into the board, right? Or if you see something like this, right, with a circle in the mid, with a circle around, again, it means the same. Vector or current points into the board. Again, the logic behind this, it's sort of like if you shoot an arrow away from you, you will see stabilizers flying away from you, right? So that's the logic behind this notation, right? And I like this picture, world domination for cats, right, the book. All right. Of course, opposite situation, if a vector is out of the page, basically towards you or out of the board, we're going to use either just dot or a dot with a circle. Again, we can use it to show direction of the current or direction of the vector. Again, the same logic. If you imagine an arrow flying towards you, right? So that's what you're going to see, right? Yeah, bad karma, right? Right. Okay, so from this point, we're going to use these notations a lot. Then cross product, vector product. Again, we discussed in our recitation classes, and we practice it, right? So I'm not going to practice it here. I will just tell you quickly the rule about this tool, and then we'll move. Okay, so vector product, it's a mathematical tool which mathematicians was introduced so that we can, physicists, right, engineers, can explain the world around us. All right, so how it works. First of all, as inputs in a vector product, we have 2 vectors. As an output, we have another vector. If as an output we have a vector, of course it has a direction and magnitude. How can we find magnitude and direction of the cross product of that vector? So, all right, so in order to find, so first of all, if you want to write cross product or vector product, we use these symbols, A cross B. All right. So magnitude can be found by multiplying magnitude of the first vector, magnitude of the second vector, and sine of angle between 2 vectors, right? You remember how to find the correct angle between 2 vectors? You need to position their tails of both vectors at the same point. And the angle less than 180 degrees is the correct angle, right? So that's how you can find the direction, the magnitude. Now, what about a direction? Direction can be found using right-hand rule. Usually I call it right-hand rule number 1, because maybe this class I will be able to introduce right-hand rule number 2, but I hope most likely not. All right, so how can we use this right-hand rule? It works this way. Okay, actually there are 2 approaches, this approach or that approach. Let's first discuss this one. First, pick the first vector in the cross product. You see A, and align your hand along that direction of A. In this case, I need to move myself sort of like this, right? So now my hand is along direction of given by the vector A. All right, so I can position my hand like this, or like that, right? Then, second step in this rule, I need to orient my hand in such a way so that I can naturally bend my fingers in the direction of the vector B. You see, vector B is sort of out of the page, out of the board, out of the screen, right? So it means that I have to position my hand like this, and only then I can bend my fingers out of the screen, out of the page, right? To get the direction of B. Because if I position my hand like this, no way, naturally, I will never be able to bend my fingers out of the screen. Or in this way, again, I cannot naturally bend. So I have to position my hand like this. So if I bend my fingers that way, so then outstretched thumb gives me a direction of the cross product of vector C. In this case, it's up. Right? So it's the first rule, I mean, the first approach which can be used to find the direction. Second approach, you can use three fingers, right? So you see in the you see on this diagram, right? So index finger, it's for vector A, right? You see vector A, this blue. Then these fingers for vector B, and again outstretched thumb is for vector C, right? So again, it will give you exactly the same results. So if I position myself like this, so vector A, index finger along vector A, these fingers along vector B, right? And outstretched thumb gives me direction of vector C up, right? So exactly the same result. All right. I usually use the first approach because every time when these three fingers, it looks funny. Right? Right. That's the only reason. That's the reason why I prefer to use all the time. I use the first approach, right? Not the second. Okay, so from now on, almost all formulas, all the fundamental laws, they're going to have this vector product. So you must be very comfortable with this right-hand rule. Otherwise, you're going to struggle on the second midterm exam and especially on the final exam. Right. So we practiced, at least I practiced in my recitation class. I spent like 10, 15 minutes practicing this, right? And if you still not comfortable, come to my office hours or office hours of your recitation instructor, right? Of course, it's better to go first to your recitation instructor and make sure that you know how to apply this right-hand rule. It's not a rocket science. It's just a simple mechanics, right? How to bend your fingers, right? Or hand, right? It's not that something, it's not that complicated. All right, so don't wait till the end of the semester and start panicking. Panic now, right? Right, and ask for help. Right. Okay, so vector product, and again, it's not the first time that you see this vector product. You've seen it in physics 1. When you introduced in physics 1 the idea of torque and angular momentum, you use this. You use this. Okay, so after this, let's move into the first fundamental law. I'm sure that you missed this phrase, fundamental law. At the beginning of the semester, almost every class I would say, let's introduce a new fundamental law. Now we're again at the same stage. We're basically laying down the foundation, but now the foundation of magnetism. And every time when you lay down the foundation, you need to introduce a set of fundamental laws, right? Again, you remember what does it mean, fundamental law? It means that you can apply it at any point of the universe, at any moment of time. Anyone can do that, and it will work all the time, everywhere. Right? No restrictions. Okay, so now we're going to introduce what is called the Biot-Savart law. I think letter T is missing. Okay, only now I realized. It should be B-I-O-T. Okay, I don't know how only now after a few years of using these slides, I realized that letter T is missing. Okay, I will fix it after the class. Okay, so this law allows us to find magnetic field created by a wire. It doesn't mean this wire is a straight one. No, it can be any wire, bent, twisted, right? Any wire. All right. And of course, since the wire is of a complicated shape, of course, we will have to write this law in a differential form. We'll have to write magnetic field created by infinitesimally small piece of this wire. Because different pieces of wire are in different conditions, right? So we'll have to write a magnetic field created by infinitesimally small piece of wire. And then if you want to find the net magnetic field created by the total wire, of course you'll have to do some complicated integration, right? But first, in order to write this fundamental law, we need to write it for infinitesimally small segment of the wire, right? Okay, so that's what we have. We have a wire, right? And we take infinitesimally small piece, ds, right? And you see, ds is presented as a vector. So what determines direction of this vector ds? There is only one direction in the wire, direction of the current. So current, direction of the current gives us a direction of this ds. Then let's assume that we want to find magnetic field at this point. It's just a completely arbitrary point. Let's say we want to find magnetic field at that point. So then we need to know direction to that point. Of course, direction from this segment to that particular point. And in order to do that, we introduce the unit vector r hat. So whenever you see symbol with the hat on top, it means it's a unit. It means this is a unit vector. It means it has a magnitude of 1. Almost every semester, if I give a problem like this about this law on the exam, I see quite a few students, okay, not many, but quite a few, who sit and struggle trying to find the magnitude of r hat. It's just 1. All right, unit vector by definition. We introduce this vector for the sake of convenience, right? Their goal is just to give us a direction. Magnitude is 1. So the goal of this vector, or the role, is to show us a direction to the point where we want to find the magnetic field. That's it, right? And of course, we will also need to know the distance from this infinitesimally small segment to the point in question, to the point where we want to find magnetic field. Okay, that's what we need to know. And then as a result, again, this is a fundamental equation. It cannot be derived. We write fundamental equations based on observations, right? So as a result, no derivation, right? And as a result, we just need to say, ta-da, and here's the fundamental law. So it's a magnetic field created by this segment at that point, and it can be found by mu naught, new universal constant. It's called permeability of free space. Basically, it's similar to the idea behind epsilon naught. You remember at the beginning of the semester we introduced epsilon naught permittivity. This is permeability. You can think of this as the quantity or parameter which describes magnetic properties of vacuum. Epsilon naught describes electrical property or electric properties of vacuum. Mu naught, magnetic properties of vacuum. The value of mu naught, yeah, here it's a 4 pi times 10 to the power of minus 7, and you see the units, right? Then a mu naught divided by 4 pi. Of course, by looking at this constant, really weird constant, mu naught over 4 pi, why would you introduce such a bizarre looking constant? And the thing is, probably next class or in a class, we will introduce Ampere's law, another fundamental law, part of Maxwell's equations. And using this mu naught, Ampere's law would look elegant, beautiful, nice, right? And you use any other adjectives, right? But Biot-Savart law looks a little bit ugly. Constant next to Biot-Savart law looks a little bit ugly, right? Mu naught over 4 pi. Then we have current. And then we have a cross product. That's why we spent quite some time in the recitation class introducing this cross product or vector product of ds, this segment vector ds represented this segment, and crossed with r hat, and divided by the square of the distance from the segment to the point in question. So where is which part of this law give us a direction of the magnetic field? This cross product. Every time, in order to find a direction of the magnetic field at that point, we need to look at that cross product. Let's quickly look. Right, so direction of ds, that way. Okay, I need to use the right hand, right? Direction of ds is that way, right? And then direction of r is that way. So I need to position my hand like this, right? And then bend my fingers in the direction of r. As a result, my outstretched thumb gives me direction of B, which is sort of out of the page, out of the screen, right? If this is direction out of the page, right? Okay, so and as I said, yeah, from now on, almost every formula is going to have the cross product. So practice right-hand rule. If you're still not getting it, come to my office hours or office hours of your recitation instructors. Right? You must be comfortable with that. And again, as I said, it's not a rocket science; it's a simple mechanic. Right? Okay, so. That's it for today, right? So what's left unintroduced? I was planning to introduce magnetic field created by an infinitely long straight wire. It's basically application of this formula for an infinitely long straight wire integration, right? But we will do it in our recitation class.